The next property, the next topic that we are going to look at is expectation and variance of random variables. These are expectation is a measure of central tendency of a distribution and variance is a measure of its spread. We will make both of this clear in this lecture. The expectation is a basic property of random variable and it is defined completely in terms of its probability mass function. What is the let us say you have a random variable x which is a mapping from omega to r and you have the experiment given by omega fp. Right. The expectation of a random variable x which is typically denoted by e of x, sometimes you might see the square brackets missing, but that is the typical notation. You will find expectation of square bracket of x is simply equal to sum over x in the range of the random variable x times fx of x. So, this is the definition of the expectation of a random variable. What is an intuitive meaning for this? The intuitive meaning for this is that you can visualize the probability mass function and view the probability masses as literal masses. If that is the case, then the center of mass of the scale would effectively be the expectation. For example, let us take the example of the single dice throw experiment. Let us take a single dice throw experiment where your x is simply the result of the first die, the result of the dice. Right. So, in this case what is the probability mass function? Well, the probability mass function would take values between the random variable would take value between 1, 2, 3, 4, 5 and 6 and the probability mass function would be 1 by 6 at these 6 points. If you can imagine the horizontal line as a scale and the masses as literal masses, then the point at which you will balance this would be 3.5 and we will see that that is exactly what the expectation of x would be. Right. In this case expectation of x would be 1 by 6 times 1 plus 1 by 6 times 2 plus dot 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 1 by 6 times 6. This is exactly equal to 3.5. This is the definition of a center of mass as you might have seen in your basic physics class. So, this is a measure of central tendency. If you had to put a center of this random variable, that is where you would put 3.5 is where you would put the center as. That is the expectation. You will see some more examples. Let us take the double dice throw experiment and for now let us take the standard counting probability measure where all 6 phases are equally likely and the probability of any event is simply cardinality of that event by 36. Right. So, if you have x to be the sum of the 2 phases, what you can show is that this the probability mass function would look like this. The probability of x equal to 2 is 1 by 36 and probability of x equal to 3 is 2 by 36, 3 by 36 and so on. Probability of x equal to 7 would be 6 by 36 and after 8 it would keep on decreasing to 5 by 36, 4 by 36, 3 by 36, 2 by 36, 1 by 36 and 0. This is the probability mass function. You can easily see that the sum of all of these values would be exactly equal to 1. This is pretty easy to check from first principles. For example, if you want to check what is the probability of the sum equal to 8, that is simply you can note down the set of all elementary events that result in the sum being 8. That would be 2, 6, 3, 5, 4, 4, 5, 3 and 6, 2. There are 5 possible events here and 5 by 36 would be exactly this. And what is the center of what is the expectation of this particular random variable? From the graph you can easily guess that the center of this is symmetric around 7 and the center of mass of this would be 7 and in fact that is exactly the case. You can compute the expectation of x from first principles here. If you did that you would get 1 by 36 into 1 plus 2 by 36 1 by 36 into 2 plus 2 by 36 into 3 plus 3 by 36 into 4 all the way plus 1 by 36 into 12. If you did the summation you would get 7 and geometrically and graphically it also makes sense that the average of the central, if you throw 2 dice, the expected value is 7 because 7 is symmetric. The probability mass function of the sum is indeed symmetric around 7 and 7 is the largest, 7 is the most likely value also. Let us do one more example. Let us say take the same double dice throw experiment, let us say y is the absolute value of the difference of the dice throw, right. So, if you have throwing 2 dice, let us say it comes 4 comma 2, the difference, absolute difference is 2, right. Absolute value of 4 minus 2 is 2. Right. What is the probability of this, what is the probability mass function of this particular random variable? Well, Fy of 0 is probability that both the phases are equal, that is exactly equal to 6 by 36. What is the probability that difference is exactly equal to 1? Well, you can note down all the events out of the 36 events, that will be 10, you will count that there are 10 possible events there and 10 possible elementary events there, and well 10 possible elements are outcomes. So, the probability of that particular event is 10 by 36 and so on. You can compute the probability mass function. You can take values between 0 to 5, it cannot take values less than 0 because it is the absolute value, and it cannot take values above 5 because the maximum way you can get the difference is 6 and 1, right. So, this would be the probability mass function of this particular random variable, and you can compute the expected value of this random variable as using the simple formula, which is 6 by 36 into 0 plus 10 by 36 into 1 plus 8 by 36 into 2 plus 6 by 36 into 3 plus 4 by 36 into 4 plus 2 by 36 into 5. If you did that, you would get 70 by 36. The expected value of the difference is slightly less than 2. Right. See, these are just some simple examples to get you running. Okay. Now, we move on to the next concept, which is conditional expectation. But before we go there, we must first define a conditional distribution. Once again, let us say we are living in the probability experiment given by the tuple omega fp. Let us say A is an event, A is a subset of omega. And x is some random variable, x is a random variable from omega to r. We can define, we know what the probability mass function is, we can also define a conditional probability mass function as follows. Fx given A of x is probability of x is equal to x given A. Right. So, if you did not have the conditional event here, it would simply be the standard PMF, but this is also a well defined thing. So, probability of x equal to x given A is the conditional probability. What is this? This is the probability of set of all omega such that x of omega equal to x given A. Right. So, here you have the left hand side and right hand side are both valid events and conditional probability is already defined. Right. So, this is the conditional PMF of the random variable x given the event A. Right. So, this is the conditional PMF, and once you have the conditional PMF, you can define conditional expectation also. What is the expected value of x given the event A? What is that? Well, that is sum over x in range of x times f x given A of x. The only thing that has changed when compared to the standard expectation is that instead of using the PMF, we are using the conditional PMF, that is the only difference here. Conditional expectation is a very powerful and useful tool, and it makes lot of reasoning, and most questions that you will be asking in practice would be of the type of a conditional expectation question. Let us have some simple examples. Let us do the example of the double dice throw experiment again. Right. Let us say you want to know the expected value of the sum of the dice, or let us say x is equal to the sum of the faces that you see, and let us say A is the event given by let us say first phase is equal to 2, right. So, that is a valid event. We can ask the question, what is the expected value of x given A? What is that? That is the question. First off, you need to know the conditional PMF. What is that? F x given A of let us say what is f x given A of 1. What is the event that the sum is equal to 1 given that the first phase is equal to 2, that is clearly 0. What is f of x given A of 2? What is the probability that the sum is 2 given that the first phase is 2, that is also 0 because the smallest phase is 1, right. So, the first phase is already 2, that is equal to 0. What is f x given A of 3, that is equal to 1 by 6. What is f x given A of 4, that is also 1 by 6. Why is that? What is f x given A of 4? What is the probability of the sum equal to 4 given that the first phase equal to 2? This is exactly equal to the probability that the second phase equal to 2, which is equal to 1 by 6. Similarly, you can compute this f x given A of 5 is also equal to 1 by 6, fx given a of 6 is also equal to 1 by 6, fx given a of 7 is also equal to 1 by 6, fx given a of 8 is also equal to 1 by 6. Everywhere else it is going to be 0, right. You can, once you have the conditional PMF, you can compute the conditional expectation the same way, which would be expected value of x given a would simply be equal to 1 by 6 times 3 plus 1 by 6 times 4 plus 1 by 6 times 5 plus 1 by 6 times 6 plus 1 by 6 times 7 plus 1 by 6 times 8. That would exactly be equal to 5.5. Expected value of the sum of the phases given that the first phase is equal to 2 is 5.5. This is a simple example. Let us do one more example. Let us say x is once again the sum of example 2. Let us say sum of x is the sum of phases, and we are once again working in the double dice throw experiment. X is the sum of phases, and let us say A is the event, the difference equal to 0. Difference, that means that effectively both phases are the same. What is the that is what A is, right. So, now we can once again get the conditional PMF. What is fx given A of 1, which is 0, fx given A of 2. What is the probability that the sum of phases is 2, given that you know that the difference between the two phases is equal to 0? The answer is this is equal to 1 by 6. So, the only event is, I mean, given the difference is 0, the only 6 possibilities are 1, 1, 2, 2, 3, 3, 4, 4, 5, 5 and 6, 6. So, fx given A of 2 is equal to 1 by 6. What is fx given A of 3? What is the probability that the sum is equal to 3, given that the difference is 0? The answer is 0, because the 3 is an odd number. You can never get, if both the die throws are the same, you can never get an odd number. So, it is 0. Similarly, you can get fx given A of 4 is also equal to 1 by 6. Fx given A of 6 is also equal to 1 by 6. Fx given A of 8 equal to 1 by 6, fx given A of 10 equal to 1 by 6, fx given A of 12 is also equal to 1 by 6. Right. Now, once you have this, you can compute expected value of x given A would be equal to 2 into 1 by 6 plus 4 into 1 by 6 plus 6 into 1 by 6 plus 8 into 1 by 6 plus 10 into 1 by 6 plus 12 into 1 by 6. Right. That would be 2 by 6 plus 4 by 6 plus 6 by 6 plus 8 by 6 plus 10 by 6 plus 12 by 6, which is right, which is exactly equal to, sorry, I made a mistake here, this is 8 by 6. By 6 plus 10 by 6 plus 12 by 6. What is the sum of this? Well, that is clearly equal to 7. Right. The expected value of x given that expected value of the sum of phases given the difference is 0 is equal to 7. Right. This is another example of a simple example of computing conditional expectations. Now, we will move on to another property of expectation, which is going to be very useful. I am not going to prove this right now, but it is a very basic property. That is, if you have multiple random variables, let us say x and y, both are in the same probability experiment, of course, obviously. In this case, we can say expected value of x plus y is equal to Ex plus Ey. So, this is the first property, expected value of x plus y is equal to Ex plus Ey. And then the second, let us say you have some small scalar, let us say you have a scalar a. What is the expected value of Ax? Right. That is equal to a times expected value of x. So, these are two main properties of the expectation. Expectation is a linear operator, that is, if you, let us say the expected value of some random variable x is, let us say 5. You can ask the question, what is the expected value of 2 times that random variable? That is equal to 2 times the expected value of that random variable, which is equal to 10. That is what this statement is saying. And in fact, the more interesting statement is that expected value of x plus y equal to Ex plus Ey. Right. So, you have that irrespective of what these x and y can be anything. Right. they can be independent, we will not come to that yet. So, irrespective of what x and y are, as long as they are both valid random variables, Ex plus y, E of x plus y is equal to Ex plus Ey. So, this is a property we will not prove right now, but this is something you should keep in mind. And this is very useful because it can help a lot in some examples which can be quite tough to get using the vanilla definition of expectation. For example, let us say you have an experiment which is the 10 coin toss experiment. You are tossing 10 coins and the random variable x is number of heads. The experiment is a 10 coin toss experiment, and let us say you have a fair coin. So, effectively this corresponds to a counting probability measure where the probability of any event is simply the cardinality of that event divided by 2 power 10, right. So, the sample space of this particular experiment is 2 power 10, right. So, you have 10 coin tosses, so you can have h all the way to t. So, that is 2 power 10 possible elements in the sample space. Let us have the simplest thing, right. So, if x is the number of heads in the 10 coin toss experiment, you could in principle get the PMF of this random variable, probability of x equal to 0, probability of x equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then you could compute the expectation. I mean, once you have the PMF you can compute the expectation. But here is the idea, here you can use the linearity of expectation idea here. What you can do is you can define auxiliary random variables. Let us say x1 is equal to the indicator random variable of toss 1 is head. Right. Similarly, you can do x2, x3, x4, x5, x6, x7, x8, x9, x10. X is clearly sum over I equal to 1 to 10 xi. Clearly you can see that the total number of heads is simply the sum of these indicator random variables. So, now Ex is by linearity of expectation simply the sum of the expectation of these things, sum over I equal to 1 to 10 Exi. But what is expected value of an indicator random variable? Expected value of an indicator random variable is particularly nice because the expected value of indicator random variable is exactly equal to the probability of that random variable taking the value 1, which would exactly be equal to half. 10 into 1 by 2 which is equal to half. So, now you immediately get that the expected number of heads in the 10 coin toss experiment is 5 without getting the probability mass function of this random variable and then doing this, right. So, this linearity of expectation is a pretty powerful tool that you will use often for computing expectations of more complicated random variables. Okay. So, now we will move to another property of a random variable, which is a variance. The variance is also just depends on the probability mass function in the same way that you had expectation. Variance however is different from expectation in the sense that variance is a measure of how much the random variable spreads out. Let us define the variance first. Let us say you have a random variable x from omega to r. The variance of the random variable x is simply the expected value of the random variable given by x minus Ex the whole square. Let us unpack this a little bit first. What is x minus Ex is a constant, right. So, once expectation of a random variable is a constant. So, x minus Ex is also x minus Ex the whole squared is a function of the random variable x, and functions of random variables themselves are random variables. So, this entire thing is well defined, that is the first thing you should understand. So, expected value of x minus Ex the whole squared, let us expand a minus b the whole squared, just Ex squared plus Ex the whole squared minus 2x Ex. And here is where you can use the linearity of expectation. So, you have expectation of some of these 3 things. So, effectively you can use the linearity of expectation to break this down further as expected value of x squared plus Ex the whole squared is a constant. So, Ex the whole squared is a constant and the expectation of a constant is simply equal to the same constant. So, that is Ex the whole squared minus 2x minus the expected value of 2x Ex. So, here is where you can use once again the linearity of expectation. Ex is a constant. So, you can take constants outside the expectation. So, if you do that you would get expected value of x squared plus Ex the whole squared minus, you can take the Ex outside and you can take the 2 also outside. So, minus 2 times Ex into Ex. So, which is exactly 2 times Ex the whole squared. So, putting all of that together you get expected value of x squared minus expected value of x the whole squared. So, this is another definition of the variance, but let us this is just algebraic simplification, but let us try to understand what this function actually means. Variance of x is the expected value of x minus Ex the whole square. The first thing you should ask is, when is the variance 0? The variance is 0 when x minus Ex the whole squared is a positive quantity, right. When is the expectation of a positive quantity 0? Well, the expectation of positive quantity is 0 only when the entire thing is always 0, which means that x minus Ex the whole squared is 0, which is means that x is a constant. Right. So, the only way the variance can be 0 is if x is a constant, which is equal to the mean or the expectation. Let us compute the variance for some simple examples. Let us say x, we have the double example would be the double dice throw experiment. The double dice throw experiment. X is equal to, let us say, first die face. What is the variance of x? Right. So, let us Ex we know already is equal to 3.5. What is the now x minus Ex the whole squared, let us call y to be equal to x minus Ex the whole squared. And what is the PMF of this particular random variable, right. So, that is probability of y is equal to what all values can this take? Well, it can take x can take values 1, 2, 3, 4, 5, 6. So, when x is equal to 1, when x is equal to 1, y essentially let us just write in terms of x and y. X can take values 1, 2, 3, 4, 5, 6. Right. When x is equal to 1, y is 1 minus 3.5 the whole squared, which is 6.25, 2.5 the whole squared. When x is 2, this is 2 minus 3.5 the whole squared, which is 1.5 the whole squared, which is 2.25. When x is equal to 3, it is 3 minus 3.5 the whole squared, which is 0.5 the whole squared, which is 0.25. Because it is symmetric now, 4 would also be 0.25, 0.2.25 and 6.25. So, y is x minus Ex the whole squared, and when x is 1 or 6, it is actually y is 6.25. When x is 2 or 5, it is 2.25, and when x is 3 or 4, it is 0.25. Now, we can compute by the simple property of x being the simple first die phase result. Each of these 1 to 6 occur with probability 1 by 6. So, you have 1 by 6 the variance would be the expected value of y, which means that 1 by 6 times 6.25 plus 1 by 6 times 2.25 plus 1 by 6 times 0.25 and so on. So, Ey, which is equal to variance of x, would be equal to 1 by 6 times 6.25 plus 1 by 6 times 2.25 plus 1 by 6 times 0.25. This would be repeating 2 times, you can just multiply that by 2. So, this is the variance of x, you can compute the value here. Okay, so what does this actually mean? Now, we have a simple example, but what does this actually mean? Let me just move this to the example part here. In this particular example, what we had was this. This was the probability mass function of the random variable x 1, 2, 3, 4, 5, 6, right. So, this is 1, 2, 3, 4, 5, 6. Right. So, you have this is the probability mass function of the random variable x, which was simply the result of the die throw. X minus Ex the whole squared is 1 minus 3.5 the whole squared plus 2 minus 3.5 the whole squared. I mean the average value of 1 minus, effectively it is measuring how far is x from its mean, right. So, 1 minus 3.5 the whole square, the average of 1 minus 3.5 the whole square, 2 minus 3.5 the whole square, 3 minus 3.5 the whole square, 4 minus 3.5 the whole square, 5 minus 3.5 the whole square and 6 minus 3.5 the whole square. So, this effectively is the squared distance between x and its mean. So, variance of x essentially measures how far is x from its mean on average. On average, how far is x from its mean? So, if x was actually a constant, then it would exactly be equal to its mean or expectation. I will be interchangeably using mean and expectation. Yeah. Mean or so if x was a constant, then x is always equal to its mean. So, it is at a distance of 0 from its mean. So, variance of x effectively captures how far is x from its mean on average. So, x variance is said to capture, it is a measure of deviation or spread. If you have a probability mass function which is spread out from left to right, then the variance of x will be large. If you have a probability mass function which is quite concentrated, for example, you can imagine 2 different PMFs, let us say a PMF, let us have the same scale so that it is easy to compare. You can have a PMF like this, you can have another PMF like this. This particular PMF is less spread out when compared to this PMF. So, you can immediately say that the variance of this random variable is lesser than the variance of this random variable. So, the variance captures the measure of spread or deviation of the random variable from its mean. Okay. So, we will now take a look at some of the properties of the variance. So, we have defined the variance as expected value of x squared minus ax the whole square. Two of the main properties of the variance are as follows. First is variance of a times x is simply equal to a squared times variance of x, where a is some constant, like for example 2 or 4 or 75 or some number, some fixed number, and you can see that y you have a squared, unlike the case of expectation where if you take a outside you get a squared here. Right. So, in the case of expectation, if you take a outside you can just get a. Expectation of a times x is a times expectation of x, but variance of ax is a squared times variance of x. And the other property is that it actually requires knowledge of covariance, but I will define that right now and we will go later. It's variance of x plus y is equal to variance of x plus variance of y plus covariance of x comma y into 2. This looks familiar to a lot of you in terms of a plus b the whole squared is a squared plus b squared plus 2ab, and in fact that is exactly the reason why you have this. But what is the covariance? I will define the covariance later when we do multiple random variables, but the key thing to note is variance of x plus y is not equal to variance of x plus variance of y. So, variance of, unlike the case of expectation where you had expected value of x plus y was simply ex plus ey, but variance of x plus y is not equal to variance of x plus variance of y.